okay? Because in principle, as an electromagnetic wave is delivering you energy, it's only delivering the energy at the moment when the electric field is large. The electric field will be a large positive, you're getting energy. The electric field is zero, you're not. The electric field is a large negative, you're getting energy. Electric field is zero, you're not. And so when you talk about the amount of energy, watt per square meter, being delivered by the electric field, you're talking about an average value. So the value for the intensity is an average intensity, so you're finding the averaged E squared, and then you're taking the square root of the mean E squared, and so this calculation gives you the RMS. So what'd you get? Did somebody plug it in? How much? 614 what? Electric field. Volts per meter. Newtons per coulomb is also fine, but my favorite is volts per meter for an electric field. Everybody follow? Yes. Tesla is a Tesla. It's an oddball combination because Teslas are related to volts per meter by the factor of the speed of light. So, I think it may be CV over speed over speed. It'll be volts second per meter squared. Yeah. That's why our good buddy Tesla gets his name after.
Is Tesla minus 12 or Tesla plus 12 for Epsilon?
Minus 12. And a minus 12 for Epsilon, no.
Oh, I wonder.
What's the number for Epsilon? Oh,
Yeah.
I'm just going to put
Next part of the problem.
I'm just going to put in my calculator.
You calculate the average magnetic field of the light.
Yeah, I guess so.
Actually, what do I mean by average here? RMS. Now, in an electromagnetic wave, since the varying electric field generates the varying magnetic field, which generated the varying electric field, they're self-supporting fields, the electric and magnetic fields have to occur in a very particular relationship with one another. Equals GD.
Okay, there we go.
Is that RMS or peak?
Peak.
Oh, yeah. Yes! Right. If you made them both into peak values, you'd raise both sides of an equation by square root of 2. So it will certainly work in RMS and in peak. So the answer is yes, this is in RMS or peak. And so I'll take my 614 over 3 times 10 to the 8. And we'll get a very small number for the magnetic field, which is 6.29, did you say?
I'm saying 2.05 times 10 to the minus 6.
2.05. And what unit?
Tesla.
Tesla. Okay, and so that's actually RMS.
Yeah.
Okay? So far so good? Now, you calculate the average pressure applied to a reflective sail.
Reflective is
2 times.
I over C.
Yeah, so we're going to have to decide which quantity gives us pressure And then the usual amount is for an absorbing sail, and then twice that is for a reflecting sail. Agreed? So pressure is what unit?
Pascal.
Yes, which is also known as newtons per coulomb. Sorry, newtons per square meter.
Yeah.
Duh. And newtons, how is newtons related to joules? Force times what is energy? Force times distance. So I could multiply this thing by meter and meter to have joules per cubic meter. So what's the pressure going to be related to?
Yeah.
It's going to be related directly to you.
Yeah.
And for an absorbing sail, the pressure is going to be equal to lowercase u, and for a reflective sail, the pressure is going to be twice. Okay? Because for any reflective thing, you first absorb it, which knocks you back, and then you throw it, and that knocks you back even further. So reflecting is twice the amount of momentum transferred to you.
The pressure is U, right?
Yes. It is U for absorbing, and it's twice U for reflecting.
So it's gonna be,
Which is the same thing as I over C. Because before, if we said that U is I over C, now for whatever reason your book goes through a very long derivation to show that it's I over C, having already shown that U is I over C. So, and every book does that. It's kind of weird. So I take my ERMS, which is 614, I square it, I multiply it by twice epsilon naught, and what do I get for my pressure? Okay? And this is actually in Pascal, which is newtons per square meter.
what? U naught is 4, 5,
Everyone agree with that? Yeah.
That has nothing to do with the size of the sail you're using?
Ah! The force will have to do with the size of the sail you use. The pressure is what it is. Okay? So the pressure is the force per unit area. By taking more area for your sail, you can get more total force on the sail. Okay? Everybody with me? Okay.
Yeah, what's the answer to part B?
SOS.
No. Oh my God.
My answer to part E is you're grounded for a centon. But that's when Battlestar Galactica was big, and Battlestar Galactica measured time units in centons, which wasn't actually very long.
All right.
Pretty lousy thing, right? Kid takes the wheel of the spaceship and heads off with whoever resting there in orbit. You know, it's not nice. So, okay. Now, calculate the size of the solar sail necessary. What would I mean by size? Area. So I would take the pressure that I'm getting due to the solar radiation and multiply it by what? multiplied by area and set it equal to what?
Force, which is GMM over R squared.
Now, this one was written as a practice problem on an exam. I don't expect you to know the mass of the sun. But for here, we can take our previous numbers. What do we have for the pressure? 6.67
times 10 to the negative 6.
10 to the
Negative 6.
minus 6
Half cup.
times the area
Half cup.
is equal to 6.67 10 to the minus 11. There's a note here that says you and your spacesuit have a total mass of 100 kilograms. That's pretty light spacesuit. Some of us have a mass of 100 kilograms without a spacesuit. Right now it happens to be roughly the mass. Yeah, the solar sail doesn't have a mass. I guess it should have said you, your spacesuit, and the solar sail. Because I don't know what you've made this solar sail out of.
Yeah, right.
I'm floating in there, and I guess
Take your clothes off and make it
Unobtainium.
knit the fabric of space-time to it. Who knows? Because there ain't nothing there.
fabric, yeah. Use your hand.
No, actually what you did was you reached into your bag of holding, and then you found all the materials that you need. Okay, so,
Well.
over how much? 150 billion. Now make the billion. 10 to the 9.
Where?
Thank you.
You don't change the kilograms to grams? Oh, yeah, because it's in the...
No, kilograms are good. Kilograms are right. I certainly do not change the kilograms to grams. I also very frequently talk about people's weight in grams. So.
How about milligrams?
Dude, you weigh 100,000 grams!
That's pretty insane.
So, what do you get for the area? It's not small, by the way.
times 10 to the fourth?
8.9 times 10 to the fourth?
Yeah.
Okay. Take the square root of that number for me. 298? Okay. That means about 300 meters by about 300 meters. Right? Because those are all in meters. So that says, if you were able to make something 3 times the length of the football field in width and 3 times the length of the football field in height, you could keep yourself from falling into the sun. Ta-da!
Pretty big deal.
It's a big step. Okay.
Wouldn't they be able to notice that before you, like, fall into the sun? It's like, a 300-meter solar cell out there, what could it be?
Well, in class, we already did our discussion with regard to Dooku
I'll just own that group.
and Dooku's sail. Okay. But actually, I learned something about Dooku this week from this one. But we won't go there. Okay. So, everybody good with this? Those manipulations seem reasonable?
What are you writing this down?
Okay. Oh, look at one of those. Aren't they cool? Okay. I own the world's most powerful laser pointer.
Can it pop balloons?
I thought the Navy
Yes, I
owns
do
that.
personally.
Does it pop balloons? Is it one of those?
Okay.
Did you make it?
You have it?
Now, the reason is, I don't have it with me. It's sitting on my desk.